So, welcome to this CQIQC seminar. The speaker today is Dr. Yuxuan Zhang. He's actually a CQIQC postdoctoral fellow, and he has been working with Yuan Zhang and me on some topics on variation of quantum circuit, and he's going to talk about this non-Hermitian physics.
Yeah, right. Thanks, Youngback, for the very nice introduction. And I've been 1 year since I first employed at CQIQ. After hosting like 4 or 5 speakers, it's finally my turn to tell you a little bit about the thing I've been working on. But before jumping into the science part, I want to first give you 2 motivating lessons that I learned during my grad school and undergrad from my physics courses that made this that sort of motivated me to start this project. The first one is you shall not pass. I'm very grateful that none of my professors actually said that to me. But what I really mean by this is Einstein's special relativity, or you shall not pass the speed of light. And the second lesson I learned was there's no such thing as a fixed future. Well, I'm certainly not talking about the stress in the test, or the randomness in falling in love, or the complete opposite way. Talking about quantum mechanics and uncertainty principles, right? It is amazing that in certain so there are like different interpretations of quantum mechanics. And the most interesting one I found is this many words here. Like this many words interpretation basically just says once you make a measurement on a qubit, the reality, there's no collapse happening in quantum mechanics. Instead, the reality just split into halves, and there's a version of you when the qubit is measured to be 1, and there's a version of you when the qubit is measured to be 0. And very sadly, we don't get to choose which path that we want to take. We don't get to select on the measurement results. But what if you're like Neo, the one from the movie The Matrix, right? And you get to select. You actually get to select your measurement results. And what superpower does that give you? Actually, this is a thing that's been studied in optics for almost half a century. I recently learned it from Professor Steinberg's group and Andy, a grad student in his group. That I'll give you one minimum example here, where post-selection can actually result in a violation of Einstein's special relativity, at least as it appears to be so. So here I have a laser that shines through a cloud of absorbing atoms, and I have a observer observing the atoms that the photons that goes through. So the cloud would I here picture the cloud as like having sort of 100% absorbing rate, but certainly I'm exaggerating a bit. But the cloud, let's assume it also has a finite response time, meaning that it would not start absorbing any photons like until a short time after the first photons hitting the atoms. This is as as for the observer, it almost appears that, you know, if you look at the center of mass of the particles, it travels faster than the speed of light, because from here to here, it would actually be the CT. But since the pulse has been sort of reshaped by this absorbing process, post-selected on the photons that's passing through the absorber, you actually see this superluminal signaling. And this has been known for almost, you know, 40 or 50 years. And then the first experimental demonstration was done in this, I think, 1982 paper. And recently, Steinberg's group also had a paper that's relevant to phenomena like this. So if you want to learn, like go to their paper. And so how do we formalize this superpower of post-selecting on the measurement results? One way of formalizing this is called the non-Hermitian formalism. So the non-Hermitian physics applied to quantum mechanics actually could be traced back to the early work of Yang and Li, C.N. Yang and T.D. Li, back in 1952. And here I just show you one minimum example where post-selection could actually lead to non-hermicity in your Hamiltonian. So if you consider a two-level atom driven by some system Hamiltonian, evolving by some system Hamiltonian, but also goes through a spontaneous decay event, where if the atom is in the excited state, it spontaneously emits some photon to some dark state, which could be measured by our cat observer. You know, the cat this time is the observer instead of being observed. If you can post-select on the event that such spontaneous decay not happening, then effectively you actually end up with a description of the Hamiltonian with this non-Hermitian part, with this imaginary part, which is unusual, but considering it post-selection could violate causality, there has to be some modification to the regular quantum mechanics that we consider in the textbook. So I'm going to give you a summary of the two main results that I worked with Yongbak and Huan. So with these variational circuits generated by tensor networks, we were able to do dynamical simulation and ground state finding, solving these two problems. And for dynamical simulation, we were able to observe a supersonic mode. I'll explain what that is, but you should think of it as the lattice version of these superluminal signaling, and which is unique to non-Hermitian systems. And for ground state finding, we were able to demonstrate that our algorithm actually accurately captures the so-called exceptional point physics, where the eigenenergy, the energy of a system goes from, if you tune the interacting parameter, it goes from completely real to real plus imaginary part. And those two, we also these quantum algorithm is also supported. They are also supported by experimental data, where we demonstrated for the first time experimentally with Quantinuum H11 trapped ion quantum computer. So to begin with, let's talk about the lattice version of the superluminal signaling. And here we actually consider a interacting fermion model. So if this term were completely real, if there were no I in this formula, then we would end up with getting like the good old XXE model or something like that. If you use Jordan-Wigner transformation to rewrite this fermionic chain to a bosonic one. But here, since we have interaction term that's imaginary, we actually have something special. Studying this interacting chain directly, analytically, would be hard, but people could use a Latinger liquid model that effectively transfer this interacting fermionic model to a non-interacting bosonic model and study its low energy spectrum. Predicted by in this work back in 2020, the authors actually showed that correlation functions sprite these correlators not only sprite according to the so-called Lieb-Robinson bound, but also sprite at a velocity that is an integer multiplier of your regular Lieb-Robinson bound. The Lieb-Robinson bound, you should think of it as sort of the light speed in a locally interacting material, beyond which you should not expect signaling to happen, in your Hermitian quantum mechanics, right? And we did check this numerically, and as one can see that when the non-Hermitian part is small, namely Jz equals to 0.3, we don't. It's hard to see any superluminum signaling, as all of the correlation function is roughly bounded by this Lieb-Robinson bound. However, if we tune up the interaction term, the non-Hermitian interacting term, we actually see that this quench dynamics, namely, like if I prepare I first don't I prepare the ground state without the interaction, and then I turn on the interaction. This quench dynamics actually captures these superluminum or supersonic behavior, if you want. Okay, and then the question is, can we do this on a quantum computer? Wouldn't it be cool to simulate a superluminum behavior on a quantum computer? Now that we have all these nice experiments in optical labs, would it be possible to do something similar for a lattice model? So here are two challenges that people face in simulating dynamics for non-Hermitian systems. First of all, there's a high resource cost for simulating non-Hermitian system. To see this, first of all, the most naive way of simulating any dynamics is to use a so-called trotterization method. That is, you decompose your Hamiltonian usually consisting of multiple non-commuting parts into small blocks and play with their commutators to try to minimize the error. Namely, you break down one big block. Certainly, you cannot do this multi-qubit interaction at once on a quantum computer. You decompose it into these small blocks of 2-qubit gates that is native to or close to native to the actual experimental device that you're using. However, now that we observe that because the Hamiltonian is non-Hermitian, so e to some non-Hermitian term, this hi plus 1 simply means the interaction term between two adjacent qubits. You have to, how do we even simulate something that's non-unitary on a quantum computer, right? Because we suppose everything in quantum mechanics is unitary. How do we even simulate something non-unitary on a quantum computer? So this could be done through this so-called block encoding by appending one ancillary qubit and post-selecting on this ancillary qubit being measured to be 0. So this actually goes back to the original motivation of considering non-Hermitian physics. That is, if you want to simulate something non-Hermitian, it appears that the most naive way is to do so by post-selection. However, this post-selection gives a exponential overhead when you consider simulating a long spin chain with a extensive time, right? Actually, this post-selection rate, if you think about this, right, every these single blocks has to be block encoded and post-selected on the measurement result. And you have to do this for multiple time slices in order to generate like a long time dynamics to be able to observe these like supersonic behaviors. So we estimated that if you want to do a experiment on roughly at our scale that we experimentally demonstrated, you need 10 to the 19 sampling overhead. And this is simply not very feasible. And this is also why people didn't simulate. So the previous results for digital simulation of non-Hermitian physics, dynamics is limited to roughly 5 spins. And even with that, they weren't able to simulate for a long time. They were only able to simulate non-interacting chains. So the way that we got rid of this problem has 2 parts. Remember that I told you that quench dynamics consists of 2 parts. The first one is you want to prepare the ground state of the non-interacting fermionic chain, and then you want to prepare. Then you want to do the time evolution, right? So we really want to squeeze the every bit out of the method that we have at hand, right? So we really want to save these like limited resource, namely quantum gates and the number of sampling shots as much as possible. So even at ground state preparation, we are already saving these quantum resources by using a compression method of this Gaussian initial state. So this is this is a technique called Gaussian MPS, Gaussian matrix product state method, that's first proposed by Fishman and White back in 2015. And the basic idea is based on the observation that if you have a free fermion system, then all of the higher order correlations can be generated by two-point correlation functions. So to prepare the ground state of a Gaussian state, it suffices to diagonalize the 2-point correlation matrix. So they also found a sequential way by exploiting the near volume law structure of these locally interacting chains. Namely, if you have a locally interacting Hamiltonian, then you don't expect the correlation to be of the ground state of that Hamiltonian to be spreading far away, right? So you actually end up with these local sequential circuits, as we also generalize this to be able to execute on a quantum computer in the 2022 result. So yeah, the resource that you need actually, instead of a direct preparation, that is L being your the system dimension, instead of being in a direct preparation, you would need L to the D. Here you only roughly need L to the D minus 1 plus some log factor. So in 1D, this means a huge saving because D would be 1 and this would be constant. And solution 2, and I think this is the most important solution that is really preventing from people from simulating non-Hermitian dynamics is a post-selection problem. So actually, one observation we made about these non-Hermitian dynamics is that even though these correlation functions could spread out in the integer multiplier of Lie-Bronson bounds, but the higher modes are actually weaker than the lower modes. So this means locality, it's still preserved in some extent. So let's go back to this plot. So this is a logarithmic scale. So you can see the first mode, it's around the correlation strings, it's about 10 to the minus 1. And here, already at the third mode, it drops to 10 to the minus 4. So you could imagine we could put a cut. Let's say we only care about roughly the third mode or so, right? And then everything beyond that is negligible. So locality is still preserved in some extent if we replace the original Lieb-Robinson velocity with a, for example, 3 times the Lieb-Robinson velocity. So if we only consider the interactions within, for example, 3 times of the light cone, that's going to guarantee you a high infidelity, a high fidelity compression of the original state, because like if there were no information to be, concerned out of that region. Yeah, and 10 to the minus 5 is too hard to be observed statistically anyway. Like because to observe that sort of signal, you need roughly 10 to the 10 sampling, right? Just from the Poisson distribution. Okay, so this is good, but how do we find the okay? It's a little bit hard to tell the colors. I should have picked a different coloring here. So how do we actually explore the possibility of this compressibility? So we use a variational method. So at each time step, like assuming we have found a circuit representation for the state at psi t, we marginally apply a layer of time evolution. This is done classically. And then using the classical computer, we can compile another circuit that represents the time evolved quantum state at next step. This is done, all classically, but you could also do this quantumly. All right, and this one single layer of application, you could do it with post-selection, and it still requires far less number of shots than if you were to do the whole thing with a post-selection. Okay, and we recently also had some relevant paper about compiling a unitary dynamics with very few samples with these quantum machine learning methods. That is related to this idea. This circuit is a variational circuit. It's a parameterized circuit. Yes. You minimize the overlap between these. Yeah, it probably should have put theta there. Yeah. So this is determined, and presumably you know the parameters from the previous iteration, and yeah, you vary these parameters. So the second challenge is that we already seen that these signals are very weak, right? And so at the first appearance, it seems like we can just keep tuning up the interaction strings. Why couldn't we just keep tuning up the non-hermicity, right? In this system, because in several plots before, I showed you that when the interaction strings was 0.3, you don't have like a strong correlation, and then now at this is, by the way, at 1.3, you have a stronger correlation. However, that would fail because the Latimer liquid is the analytic model that we use, namely the Latimer liquid model is a effective theory, and it would fail beyond if you tune up the interaction strings to be too strong. So seeing that dilemma, we could only hope that we use some data processing scheme that could, potentially contribute to a better quality plot, right? So we use these error mitigation schemes that's first proposed in this NatureCom paper by Google Quantum AI, where they because the model we considered is if you write the Jordan-Wigner transform Hamiltonian, it preserves the total charge, the total U1 charge. So it makes sense to exploit that symmetry because it's your state is now involving in a subsystem in the subspace of the Hilbert space. It makes sense to exploit that symmetry. So this is a gate that is the most general gate that you can write down for any state that involves in a U1 preserving state subspace. So we use that as our variational gates. Now this has two benefits. For one, it reduces the number of parameters from a SU4 gate, namely 15 parameters, to merely 5 parameters. And secondly, it preserves the total charge of your time evolution. So you know that if your measurement, if a measurement output string does not preserve the total charge, then you would know this is not due to the imperfection of the variational compilation, but due to the noise within the actual hardware execution. So we can just do this like cherry picking in our collected data and discard anything that's non-charge preserving. Also, we observe that these supersonic modes are supposed to be a collective behavior of all the bulk sites. So when reporting the actual correlation function, we did an average over all of these bulk sites. Instead of like, people previously only picked like certain correlation functions between like certain sites, but rather we see this as a huge race, right? Because you're simulating, like you're reporting a whole correlation matrix, but you're only reporting a slice of it. So I show you two plots here. The top one is what would have happened. It should be had roughly 20 times more quantum allocations, quantum resources on the project, right? But we didn't have that much of resource. So this is a 18-site chain. The quench dynamics is performed, and we report basically this density two-point correlation function, but averaged over all of the bulk size. And in the actual experiment, we actually only picked two slices, and we actually this was t equals to 1 and t equals to 2. So not sure why it isn't showing here, but the Lieb-Robinson bound at t equals to sorry, I think my Zoom just updated itself, and yeah. What's the meeting ID? Yeah. What's the meeting ID? Sorry. Okay. Find it here.
Paste it on the cloud.
Yeah, what's
So I give it.
oh, you gave me the Zoom link?
I give it to you. Yeah.
Okay.
Yes. Is everything okay?
It wasn't for minutes, but I think it's fine now. Okay. Yeah, my laptop just wanted to update Zoom for no reason. Okay. Oh, sure. This is the wrong one.
All good?
Thank you. That's some signal of supersonic mode interfering with my laptop. Okay, so as compared to previous works, they only did like 5-qubit simulation, and it requires like 160K samples, and we only did this with like 5K runs. That's the power of variational circuits as applied for non-Hermitian simulations.
How do we see the signature of the supersonic and the Yuxuan Zhang?
Oh, this one. So here, this is basically the first peak. This is basically the like the peak you would see like here, and this is the second peak. This is correspond to the first supersonic mode. Okay, and the Lieb-Robinson bound, it's a shame that I plotted in light blue color, and it's not showing up here. It's like here. The Lieb-Robinson bound is like here. Yeah. So if this were Hermitian, you should only expect signal within this region. But now you see like signals here. Okay, I showed you the dynamical part. Now, as I promised, I'm going to show you the steady state preparation part. So this is a variational quantum eigensolver for non-Hermitian systems. So very unique to these like non-Hermitian system is the spectrum theory would fail. That guarantees that you have like real numbers in your eigenvalues, and that guarantees that your left eigenvector is a Hermitian conjugate of your right eigenvector, right? And instead we have this like bi-orthogonal relationship that exists between left and right eigenvectors. So if you just run the for example, if you just run VQE naively, you actually end up with getting a linear combination of different eigenstates, which messes up with the normalization. So instead of doing the energy minimization, which is a scheme considered by many Hermitian systems works, we consider this variance minimization. So for these like non-Hermitian spin chains, like for example this dissipative eigenmodel that's studied in this 1991 paper, instead of minimizing the energy function, we minimize the second momentum of the Hamiltonian. Basically, we say that not only we have parameterized quantum circuits, we have one more parameter that is the energy, and we try to minimize this Hermitian conjugate minus E star times the Hermitian conjugate of that. And if this objective function is 0, you're guaranteed to have some eigenstate. You're guaranteed to end up with some eigenstate, with E being its respective eigenvalue. Okay, and on some previous results considered by this 2023 paper, they're conducting numerical simulations on this variance minimization scheme, where they were able to do a 7-qubit chain and capture a so-called exceptional point transition. Namely, you see here, as you tune kappa, let me remind you, kappa is the strength of your non-Hermitian field. You actually go through a phase transition between having all of your having no imaginary part in your energy to your to a splitting of the energy into complex conjugate pairs. Okay, so but their method also has a few drawbacks because first of all, they did a direct encoding. Namely, they mapped one spin to one qubit, and that really limits the number of qubits they can simulate with a classical computer. And the second drawback is loss function. When the loss function goes to 0, it returns some eigenvalue, as I said, but not necessarily the desired one. So when the system size becomes really large, how do you control like which eigenvalue you're gonna end up with getting? Right? If you just random guess some value, it's very bizarre that, you know, very likely it will return the false eigenvalue that you want. So since we now want to find the ground state energy, for example, we did define the ground state as the state, the eigenstate with the minimum real part of the energy value. We come up with we borrowed ideas from Hermitian systems and tensor networks. We borrow these ideas called matrix product states. The idea is basically, you know, if you have a like I said, low entanglement state, when you look at this Schmidt decomposition between two partites of the quantum state, it's gonna have a low entanglement entropy, and thus you can throw away a lot of these Schmidt values. And if you do this sequentially for your quantum state, you end up with this so-called matrix product state representation. And further, as many previous work show that for any matrix product state, you can actually turn it into a so-called sequential circuit or a QMPS representation. When you put any MPS into the so-called right canonical form, you actually end up with each tensor being in isometric form, which you could then embed into unitaries. And you could then design the unitary circuit for representing the state. So the good thing about this is you don't have to store the whole state all at once. And if you look at the circuit here, the physical qubits, after applying certain, this UA basically is one of these blocks, right? After applying this block, your physical qubits could be measured and reused. This intuitively it means all of the correlation, all of the entanglement details is stored by the bound qubits. So the physical qubits could be reused. So to represent a L to the D system, you actually only need L to the D minus 1 number of qubits, and this is, we've seen this in the GMPS construction as well. But you know, it also applies to these non-Gaussian states. That's the point. So solution 2, that is to the challenge where we don't have a, you know, we have some eigenstate, but not necessarily the desired eigenstate that we want. We design this iterative warm start method. So the idea is basically you start with no imaginary field, do your good old VQE for this Hermitian problem, and you marginally turn on the imaginary field, and using the previous optimized parameters as a initialization. This is some idea, that's, you could say, partially borrowed from machine learning as, this as a transfer learning idea. So yeah, we repeat this process until the desired imaginary field strings is reached. So I'm going to show you some results here we have for simulating the non-Hermitian spin chain at 19 and 20 system sizes. So we set this to be j equals to -1 to be ferromagnetic, and then remarkably, using this quantum tensor network method, we were able to store the correlation in merely 2 + 1 qubits, 2 bound qubits plus 1 physical qubit. And we capture this exceptional for looking at the n equals to 19 case. This actually captures the exceptional point transition for various different, different interaction strings. Okay, and this straight line is the MRG result, and these with error bars, these were experimental results, and these squares. Sorry, the lines, they were numerics. They were numerics. Okay, and another signature that you can tell from this plot is one interesting about non-Hermitian system, that it does not go through a EP transition when the number of sites is even. And this is due to the D2 symmetry of the model that we picked. And the ground state and first excited state would belong to a different charge sector for a for even number of sites case. And they would not form a Hermitian conjugate pair in that case. And we also compare the correlation function compared to these like ED results. Sorry, DMRD results, I mean. And one more thing is, actually, if you look at the marginal error of the energy that you simulate with these tensor network methods, you can actually see the different peaks when there's an EP transition for these n equals to 19 cases. So you can see this one corresponds to where we have the first non-Hermitian, the imaginary energy here, and this peak would correspond to this point here. So this set of work actually leaves us a lot of open problems. So I think the first result can be regarded as a quantum advantage of universal control for simulating non-Hermitian dynamics. So let's say if you were to simulate non-Hermitian physics with an analog quantum computer, then there's no control over what gates that you can apply. Then you have to do post-selection. The idea is a universal quantum computer allows you to avoid post-selection in simulating such dynamics in some cases. However, we also analytically prove a no-go theorem where even some Hamiltonian consisting of the form that's like H equals to sum of I times Z, for example. Even simulating the dynamics of this Hamiltonian on certain initial states could be could be exponentially hard to compute with a quantum computer. So where is the boundary? Where should we draw the line? That is definitely the first big open problem, and that actually also says something about, you know, when non-Hermitian physics should be considered physical. I think that's opens at least gives some hint to a very rich field. Our second result, namely the ground state preparation result, suggests that these quantum tensor networks can be extended for non-Hermitian systems, but also in Hermitian system, there's you could define entropy, and the hardness of representing a state with these quantum tensor networks is directly related to the entropy entanglement laws. But how do you define entanglement in a non-Hermitian system? This is another big open problem, I think, that is worth studying. And with that, I want to give a shout out to my advisors, Yongbek and Juan, and many of you guys that I talked to with group meetings that I crushed, and, you know, had inspiring conversations. Thank you for your attention, and I would take any questions.